Hello guys, so today we're going to be integrating sine of x over x going from 0 to infinity dx. Now this is known as the Dirichlet integral and it doesn't have an elementary solution. So what that means is that if you integrated this with no specific bounds, so basically an indefinite integral, you will end up with something that cannot be expressed in terms of logarithms, trig functions, inverse trigs, or hyperbolic trigs, or exponentials, algebraic functions, etc., etc., etc. So, for example, the gamma function or the logarithmic integral are examples of non-elementary functions. So, if that's the case, how can we approach this problem? Well, we're going to be using what's called Feynman's technique to approach this problem. And the basic idea is that you introduce a parameter, t, a, whatever you want to call it, and then you introduce the parameter in such a way that when you take the derivative of the integrand, you end up with a very convenient integral that you can integrate properly, and then you construct a differential equation using those values and then solve the differential equation to find the value of sine of x over of the integral we're trying to find. So in this case, we're going to be defining the function as the integral going from 0 to infinity of sine of x times x, sine of x over x times e to the negative xt. Now, why did we choose e here? Because if you take the derivative with respect to t here, x is a constant. We're going to be getting to that later. The x's cancel out, and we end up with a pretty nice integral. So basically, we're looking for f of 0 here. Also, because if you plug in 0 instead of t, you end up with 1 here, and that's the same thing as the integral beforehand. And also, one more thing about the differential equation we said that we're going to create. We need to find a convenient value for the constants, because if you solve a differential equation, you're definitely going to end up with a constant of integration if you don't have an initial condition. So let's create an initial condition here. So if we say f, well, this is actually not the correct way to express it. If we say that f of t as the limit going from as t approaches infinity here, we can say that this is just going to be 0, and 0 times anything that's not infinity is just 0. So we can say this is going to be the integral going from, this is the integral of 0 dx. So just 0. Or if this notation confuses you, you can just say f of infinity is equal to 0, like this. So let's get to the actual differentiation part. If you differentiate with respect to t, now you can just write this down as f prime of t, but the other side is going to be a special case because we're differentiating under the integral sign. So we're going to have the derivative with respect to t going from 0 to infinity of sine of x over x times e to the negative xt dx. So whenever you have a derivative outside the integral, you can just put the derivative inside of the integrand as a partial derivative. Because if you do that, then you're not going to be affecting x in any sort of way, and you're just going to be affecting this value, which is supposedly a constant in the case of this integral. So let's just quickly go ahead and do that and differentiate under the integral sign. So sine of x over x is a constant, so we can just write this out. And e to the negative xt is the only thing we're actually going to be differentiating in this case. So this is what we end up with. So if you differentiate e to the negative xt, you'll end up with negative x. Again, we're differentiating with respect to t, and x is a constant in this case, so negative x times e to the negative xt is what we end up with. So e to the negative xt times sine of x times, I'm going to be writing this down as x to the negative 1 for convenience purposes. And this is just equal to n times x, because we took the derivative here. And that's basically the result here. So we can cancel out this x over negative 1 with x by using properties of exponents. And we end up with the negative integral going from 0 to infinity of e to the negative xt times sine of x. So this is actually a pretty classic integral. It's actually just the Laplace transformation of sine of x, which is equal to 1 over s squared plus 1. And of course, this is if s is a complex argument. So in this case, t is our argument. So we can say that this is equal to negative 1 t squared plus 1. And this is equal to f derivative of t, which is pretty nice. Now we have our differential equation over here. No quote-unquote differential equation, actually, because it's not actually a differential equation. So if we integrate both sides here, so negative 1, this is with respect to t, because the function we're integrating is with respect to t. We're integrating both sides. And if you integrate f prime of t, the integral and the prime cancel out, and you're left with f of t. And this is a pretty well-known integral. It's just negative arctangent of t. And of course, since we have an integral here, an indefinite one, we have to put a plus c here as our constant. And this is equal to f of t. Now, we determine this initial condition here. The limit as t approaches infinity of f of t is just equal to 0. So we can say negative arctangent of infinity here plus c is equal to 0. Now, arctangent of infinity is a pretty convenient value, and it's equal to pi over 2. So we have negative pi over 2 here, and c is equal to pi over 2. Now that's great. And if we substitute this back into our equation for f of t here, we have negative arctangent of t plus pi over 2. So what were we looking for originally? Well, we were looking for f of 0. So if we substitute in 0 over here, f of 0, we end up with pi over 2 minus arctangent of 0. And what is arctangent of 0? 0. So we can just get rid of this, and we end up with pi over 2 as the final answer to this integral. Now, as a bonus, since this integral is an even function, we can say that the integral going from negative infinity to infinity of this same integral is just going to be 2 times this. So 2 times pi over 2 is just pi. So this is a neat little bonus here. And this is how you integrate sine of x over x dx going from 0 to negative infinity and going from 0 to infinity dx with the Feynman technique. Thank you for watching.